Well, welcome back, everybody. We're trying to get everybody in. Most of the people like the coffee that much that it takes some time to get them in. So I think one or two, three, four, five people will come in. But we're going to start with the program. We're 3 minutes late on schedule, which is not really a problem, but we're going to do the right thing. I hope you had a nice coffee break and good conversation about what you've heard today and what you're going to hear for the next speaker. Thank you for being back. The next speaker, Wojciech Wegrzynski, Building Research Institute in Poland. He will introduce himself when that is needed because he's a best influencer, makes his own podcasts, and is really known in the world of fire safety and science. Wojciech, floor is yours.
This red button is really tempting. Thank you very much for the invitation. I have been here last year during the giving the workshop. I'm very happy you've chosen to invite me again. I'm not sure if after this talk you'll choose to do that once more in the future. But again, as a fire engineer, giving these two data points, workshop last year, keynote this year, we are all used to extrapolate from incomplete data sets the lack of physical evidence. It seems that my future here is bright with this trend. I was asked to introduce myself. I am a professor at the Building Research Institute, ITB, in Poland. I'm a fire scientist, and I seem to be some sort of influencer. This means that for a scientist, my Kardashian index, which is the ratio of followers to citations, is ridiculously high. And I'm not sure if this is because I'm a good influencer or a horrible scientist. Anyway, I try to do research on the built environment, on fires in built environment at different angles. And I'm very, very lucky to work where I work, where I can really touch these things from different perspectives, which lead me to the presentation that I am about to share with you, Fire Safety Engineering, the Unknown, and the Race Between Safety and Novelty. And in this presentation, I would love to try and answer, together with you, some questions about why fire safety is a key to a sustainable future, why are we racing against these damn innovators, and why in this particular race, if we lose, both teams lose, and that's a bad outcome. Also would love to brainstorm with you, how do we navigate this world where the data is scarce and evidence is old or incomplete. So I think it's going to be an interesting journey. I hope this. I would like to have you, in a way, participate in this exercise, at least through thinking, through thought experiments. So I thought I will warm you up a little bit with fire safety engineering quiz. So if I show you these three materials, which of those you would associate with the worst fire? If you thought timber, you're probably already ahead of most architects in the mainstream media, because from what I read in architectural journals, the steel is perhaps the worst, and timber chars and doesn't burn, which I will perhaps address a little later in the talk. But if you thought timber, I guess your reasoning for that is based on the material science and the fact that combustible materials and fires usually lead to a bigger and worse fire outcome. And I would second that way of thinking. So if timber would be the worst, let's focus on another scenario. Let's say we transport it. Which of those would be the worst fire risk? Yeah, I guess the third one, because as fire engineers we understand that the porosity of the material, the surface area of the flammable material, the way how air can penetrate the truck, makes the third hazard really outstanding from the others. It's obvious, intuitive for us that this particular scenario would end up in the worst fire hazard. So this was all simple, but let's shake the environment a little bit. How about now? Like, if we park the truck, like now it's not that obvious anymore, right? So the left one, I mean, not a good chance that all tankers will catch fire from the boy in the middle, but if they did, that's gonna be a really like low probability, high significance fire. The middle one, I mean, it's not gonna be a huge fire because it's planks, but statistically, this one will end up with the most damage every time it burns. And the third one, okay, that's the biggest fire, but it's outdoors, it's not a big threat. So it's not about just the materials that we are using. It's not about what we do with these materials that we're using. And it's not just about where we are using it. It's about all of these things all together. And this makes discussing fire safety in the world of continuous innovation very difficult, because many stakeholders would like to focus on one particular aspect of this puzzle, where all of them are perhaps equally important in solving the major problem. I would say it's in the problem, or the issue is in three layers. It's in the product layer, in the material layer, and the fact that it's a separate layer is an issue on its own. If you think about the products, they're often certified, they are compliant. And people who bring these products to the market, they only have incentive to act on this layer. They do not have incentive to act on a building layer or on an assembly layer, because they're not certifying buildings, they're certifying products. They want to put the product on the market shelf, and their responsibility ends here. The second layer, assemblies, so how we put the materials together and form a larger parts that then constitute our buildings. This usually has no owner. That's a construction company that builds that, but the construction company does not certify its construction during the build. It has to be designed according to regulations, and it has to be executed as per the design. And then you have the building layer. The building layer where the whole building and the environment in which the building is placed is the battlefield where the eventual fire will take place. And we also, to some extent, design these buildings, but it's difficult to say we certify or do other things to them. Now, all this puzzle together, this is the fire safety of your building, from material to the building level, where different actors would act a different way. And I would like to take this slide to also reintroduce myself, because in my institute, I have the unique opportunity to work at all three levels. So we are a certified laboratory, accredited laboratory. We do tests and certification for all types of fire-related products. So we have extensive experience in testing and delivering certifications for products that go into market. Per assemblies, we are a research institute. We purchase those materials, we put them into assemblies that are then burnt and tested, and we try to learn with that. And on building level, we are designers. We design buildings, we do full-scale tests in buildings, we are participants in commissioning processes of buildings. We act as a third party in buildings. So we also have experience from the building perspective, which combination of those three gives me perhaps a different view on what the problems in the space are. So if you think about how innovation happens, I like this innovation cycle, which shows how it should happen. So let's start with the new technology innovation, or a fire that has surprised everyone. And from this, we understand that we have some issue. We're engineers. What engineers do, they engineer a solution. So faced on the issue, we try to find a solution for the problem. Now, to make sure the solution is correct, we want to verify the solution. So we would always also go to experimental verification of some sort, maybe some simulation tests, whatever you use to verify your solution. And once we confirm this point, we disseminate the results of our solution, first of all on the building that we were talking about. But then again, our solution may be a starting point for someone else on a similar building object with a similar problem. And that's when the solution spreads in the environment around us, where people start to accept it. And eventually it reaches maturity where the solution we worked out is the new normal. It's the standard. It's in the law. It's codified. And everyone is using that up to a point where we face a new issue. So I would claim that for a great chunk of the history, the innovation cycle would be like that. We would face the cycles of innovating, standardizing, and facing new issues. The problem today is this doesn't work anymore. It's happening too quick. If we reach this point, we're already good, and often we stop at this point. That's why it's not just fire safety. It's not just innovation. It's really a race between those two. The speed at which people innovate for good reasons is unparalleled to our capacity to research. So we need to find ways how to navigate this landscape in these circumstances, because we're not able to change circumstances. We cannot tell the world to slow down. Elon Musk tried to tell the world of AI to slow down, and well, not really happening. So we cannot be Elon Musk. Come on, guys. We cannot tell the world to stop because we need to solve our stuff. So I also feel that it's not always a race. Sometimes it feels like, pushing the line, because the forces of innovation that respond to other needs than fire safety usually take our solutions in the opposite direction than where we would like to take them with fire safety. I feel that whenever we find a new brilliant solution for a certain problem, it usually ends up horrible in fire. But that's a thing that we need to be aware of, and that we need to solve for our colleagues working elsewhere in the society. So let's try to talk about some innovations. Let's try to talk about some novelty. Let me take you to my innovation town, where we are going to innovate and discuss fire safety as we go. Let's start off with compartment fires. In my podcast some weeks ago, I had the massive privilege to interview Professor David Purser, the toxicological master of fire, the most renowned toxicology scientist in fire science. And what he told me shocked me. He said that 40s, 50s, the fires were not that toxic. And I'm like, well, that's not very chemical, isn't it? Like, fires are toxic because they produce toxic products. But that's not the point. The fires were not considered that toxic because you had lower amounts of smoke-producing fires because the fires were slower. You had less amounts of combustible materials, both expressed in the mass of the combustibles that we have now in our houses with all the plastic appliances and all the foamed products that we use all over our spaces, and also through the fact that the effectivity of combustion of these things increased. So there's simply more material, and it's more combustible, which ends up in the larger fires. I really love this comparison of old versus new performed by Fire Safety Research Institute. I've heard Robin was doing this test, so if you want, he can tell you more about this comparison. And what it shows, a room with old furniture that is built with natural materials, and a room with modern furniture filled with synthetic materials. And as you can see, more materials, more flammable materials leads to worse outcomes. Fires are growing exponentially, but they also grow in certain events. If you reach the flashover, it's a flashover. You have a very large fire. If you don't reach flashover, you don't have it. It's a smaller fire. It's easy. So when people see these types of comparison, they see, okay, yeah, now the modern fires are worse. It changes. But I would like you to point into very different thing. What I see in this picture is the change. And what I see in this picture, on the left, I see the fires that perhaps Philip Thomas saw when he was building the foundations of our discipline. These are the fires that Kunio Kawagawa saw when he was finding out that there is hot smoke layer and cold layer in beneath. These are the fires that the foundation fathers who set the cornerstones of our discipline saw, and these were normal fires to them. They didn't even have knowledge of existence of the fires to the right, which are the normal for us today. And our whole discipline is based on this beautiful research from 70s, 80s, where the foundations were set and we're building on top of them. I'm not saying we should question that, but we should understand that the times have changed. And what has been known perhaps is not obvious or is not normal anymore. The same goes into other aspects of fires. I Googled mass timber fire experiments. You get these beautiful images of fantastic work carried over the world. And if you look at all of these experiments, what do you not see on the picture? These mock-ups do not have windows. Why? Because if you research compartment fire, you have to have a design fire for it. And often, the worst combination of an opening factor, which is the ratio of opening to the wall surface of your building, is associated with the highest temperatures and perhaps the worst fire outcomes. So in fire experiments, because we assume that the glazing will eventually fail in a flashover fire, we assume that it will lead to growth of the biggest fire, and these experiments are already expensive enough to not put hundred thousands of euros of windows into them. And what this leads to is a world where this very important research perhaps is not fully representative of the real world conditions. Because today, the windows that Philip Thomas was looking through were a single layer float glass, which got to 200 degrees and just fell off. Today, we're living in a world where residential units have very sophisticated multi-layered plastic windows, which just refuse to fall. And in some of our experiments, they were very at the point where in my FDS simulation, my FDS would throw them away because I broke the temperature point. But in reality, what we ended up with a very long fire, and it started growing again as soon as the rubber gasket melted, and the window just slid out. It didn't break. So the whole assumption is a little different. It's not exactly the same fire. This will lead to completely different outcomes. And if you think about what's the worst fire scenario you can have, is it really the highest intensity short fire, or perhaps a very long-lasting medium intensity fire, or perhaps a traveling fire? We know there are multiple scenarios, but for some reason we are not really putting this knowledge into action. So yes, compartment fires on their own have changed a lot. The second thing, perhaps my favorite, facades. So, boy, facades have changed in the last 30 years, and they're a place of massive innovation. One thing that we tend to not really take in consideration is that fire is just one of many objectives that facade people have to take into account, many. And as fire engineers, we're very bad in communicating in a way that we take information from others and give our opinion. We usually try to evangelize them that fire is the worst thing, you need to defend against fire. But we tend to not listen to them, that they need moisture control, they need wave, they need exposing certain views of the building. They don't take into account that it's a beauty feature of a building. From Roman times, the beauty of the buildings was one of the main features of a building, and it remains till this day. And this beautiful building is a statement to that. There is needs for biodiversity. There is need for preventing from wind, noise. A lot of objectives, fire being one of them. And perhaps all the things that work well for others don't work that well in fire. And we had some very striking examples of how space was innovated without the fire puzzle and eventually ended up in the disaster. And taking the casualties and all the pain the Grenfell Tower did to the victims, an important thing looking at the build industry. If now in the UK they have to or want to remove multiple facades from multiple buildings, I'm sorry, I don't care how sophisticated, beautiful, and carbon neutral the facade of the building was. If you have to take it down and replace it, it's nowhere sustainable and definitely not in the circular economy. And these are the consequences of not having the fire puzzle. This is an example of how we failed a race, and both parties lost because the innovation went too far. Now we were, in hindsight, we were trying to find, okay, could we point to this with the data we had? We did a very interesting study with Imperial College London and Matt Bonner, who was doing a PhD at the time, where we took 267 tests carried out at ITB on medium-sized facade samples. And we've applied the new statistical methods to investigate them and seek, could this database really point out the bad solutions? What we did is not do that through the standardized means that the test includes. Because if a measure becomes the goal, it stops being a nice measure. We invented our own measures. And we immediately saw from our database, yes, there are solutions that are outstanding as perhaps more flammable, worse. I'm not saying bad, but they stand out as different. There are solutions that are not different. So we did this, then we followed up into a very large experimental program when we were just burning tons of facades, medium scale, with different features, comparing materials, but also the ways how you build them. And trying to investigate like what are the features that make these things worse. Okay, it's a little late after Grenfell, but better late than ever. And a striking thing that comes up, it's not just about the material. It's a lot about assembly. You could make, to some extent, flammable facade, which behaves quite well if you remove the cavity. And this video is a very nice comparison how the behavior changes when you remove the cavity. So if cavity is an issue, we can engineer around that. We perhaps can find a solution. Then I also thought like how we missed this on our radar with all the fire science we know. And if you go into like a scientific explanation, we perhaps know how to solve flame spread in opposed wind condition through fundamental laws of physics. We also understand that if you rotate the thing and add gravity to the factor, you have a different modes of heat transfer that happen and a completely different flame spread. And we also understand that if you put a barrier in there, of course you increase the complexity of a problem, but the problem itself changes. We can do that from fundamental laws of physics. And we also now have multiple groups who are doing that experimentally to seek like at what level of the cavity it becomes a problem. Spoiler alert, the exact ones that we like in our buildings. That's a little issue. But today we've turned the issue, perhaps a little late, but we've turned it into a scientific problem which we research and we try to find scientific answers on how to build this properly, because just banning everything on our facades is not going to work. Today we have amazing, amazing efforts. Sorry. Did I run out of time? I put a coin in this? I can continue for 30 minutes on this slide. Oh. That's interesting.
Just a minute.
Should I entertain you in some way? I'm taking those minutes, by the way. I'm taking account of that. He was really pushing on time with me, and we were already started 3 minutes late. I've noticed that.
We'll take that into consideration.
Oh, yes, you will. I was on a slide like 17 out of 300. Oh, yes, that's the slide. Yes, it works. Fantastic. So, I mean, at this point, facades are not a novel problem anymore. There is so many people working on facade fires. There are brilliant, brilliant minds trying to find solutions for facade problems. We have a new standardized method coming for facade systems. I mean, facades are, in a way, sorted. I mean, it's really low chance that we will be surprised by this problem again, right? Yeah. So, in some sort of way, we're repeating the cycle, but of the bad innovation. Because we put cavities, plastics, install them on tall buildings, and to spice it up, we put herbs on it, which can be dry and promote fuel load. And that leads to perhaps fires like this. This is a real-time footage, 5 meters tall facade. A little flamelet touched the plants. And soon you will see the magnificence of this rig in this video. And perhaps the fact that plants burn this quickly is not the worst part of this experiment. The worst part is the fact that there is a cavity behind the pots, and the pots themselves are plastic. We're again at the same problem, and it's not a surprise that we end up with the same outcome of the fire once these parts of system become involved in the fire. Like, it's kind of obvious it's going to happen, and yet these things are installed on our buildings without us participating in fire safety designing them. And if we put them on our plot, they are very close to the outliers of the previous research we've done. So perhaps we should have seen that coming. So next part, something that was already discussed a lot in this Congress in the brilliant previous presentation. Let's turn our buildings into power plants. This is not a novel challenge. Generating fires in an infrastructure of energy is not a novel problem. There's a whole industry that worked that out, and trust me, they really care about fire safety. So in our buildings, we want to generate energy, we want to transport it, we want to store it, and this brings us into many problems. First, the roof behavior that changes with photovoltaics. The two I want to talk about, and cable fires. With the roofs, you take a fairly safe photovoltaic panel that's certified, you put it on a fairly safe roof membrane, which is certified, and you come up with, inferno, like on the picture behind me. That's a research from Jens Christensen from DBI, who's researched this for his PhD and produced beautiful outcomes investigating the impact of gap and the angle of the membrane materials and showing in which scenarios this leads to worse outcomes and where it leads to not so bad outcomes. And is this a problem? Yes, it is. I mean, I don't want to throw stones, but you had a fire that looks like awfully like this one. I'm not saying we should have seen this coming, but yeah, kind of. For cables, there is a lot of research on cables in power plants. That's the main thing in power plants. You research the damn cables because they are the main source of fire hazard. And we do that. And now, the thing that scares the hell out of the power plant people, we just put them in the shafts in our residential buildings because you have to transport 2 megawatts of energy from your PV facade to somewhere, right? And we just go and do that without really touching the experience of our colleagues from other disciplines. Next one, electric vehicles, another everyone's favorite thing. And I've talked about it a lot in the last time I was in here. And here, I have an example of how we approached it. Before we knew what are the fire scenarios for electric vehicles, we already started to explore what would happen if a certain fire happened in a car park of a certain size, to identify which car parks are more likely to be good in such a fire and which car parks are a problem. So there's a whole recording of the last workshop, if you like. But this is one part of the hazard. Now we understand there's another part, light vehicles. IFAB did brilliant research on electric scooters and the fire sizes, and they've shown that the e-bike can generate a peak heat release of 1 megawatt. That's what does a flashover in a room corner test. That's a very large fire. And in your country, you tend to stack those things in multiple levels next to your railway stations. And I'm not sure if this is a fire scenario that anyone thought about so far, and it's coming our way. Next thing, mass infrastructure. By 2050, 50% of the population will live in cities. So we will need very efficient mass transit. There's a whole space where we try to create safe mass transport infrastructure. And in ITB, we're researching that a lot. I'm actually going to speed that video a little bit. in the current paradigm, we try to achieve the level of critical velocity where we control the fire. My question in innovation in this space, we spend awfully lot of money achieving that. I'm not sure if it's necessary. It's somewhere we innovate. But I would say we have tunnels covered. Like, we know what makes a bad tunnel. Like, if your tunnel is small, if you don't have evacuation routes, if you have bad lighting, if you have bad ventilation. I mean, these things make tunnel a horrible place. And we've learned to not build these types of tunnels, right? Sorry, 1 second. Yeah. So with new concepts, like Loop in Las Vegas, what they're building is a small networks of tunnels underneath the city where electric vehicles like this one drive through. And essentially, it's a metro system in which the vehicles are rolling stock. I don't want to be sued by them, and I don't want to shame them. I have no idea what kind of novel safety features are introduced in these tunnels, and I would love to learn about them because they seem invisible. I cannot tell from the video. But in general, perhaps this is the summary of the worst things we know about tunnels, and yet these are being built in our cities. Next thing, timber, mass timber. We need to have lower CO2 footprint on our environment. We need to reduce the carbon footprint, and a great way of doing that is by introducing mass timber into built environment. And we do that, and when you read the literature, not the literature, when you read the papers, the magazines for architects, you will learn that fire chars, it has better fire resistance than steel. And in general, it's not a problem because we know how to handle that. Oh, and it's predictable. That's the best. I'm a fire scientist for 13 years. I have no idea how this burns. And these architects say it's predictable. Amazing. I believe this is the approach of the industry because we are telling them where the problems are, and they choose to ignore us. It's not lack of communication. It's not lack of information. It's a choice that we're being ignored. And trust me, if a major building burns down, it's going to be our fault. We failed the society, not them. We need to think about it, how to break into their world, break by listening to their needs and finding out how they optimize their buildings, what they want from a building, and put our puzzle that will introduce safety into their concepts. We cannot do that by telling them timber burns, it's bad, you cannot do it. We need to educate them how to do it well. It's difficult because they come into some concepts that, in my opinion, are like, if I think about, a low carbon footprint building, I think about simple walls, encapsulated, maybe exposed ceiling. That's nice. But turning, like the one on the right, I would actually like that in my experiments because it takes away the crib building part in the fire experiment, which is quite annoying. But yeah, we need to explain that to them. Timber comes with many problems, multiple problems at different levels. I would touch briefly on two of them, fire spread and fire resistance in this talk. So we've done a lot of research with OFR for the large Structural Timber Association. These are producers of CLT, and I really appreciate that they choose the path of research and investigation and understanding their product, because I think that's a mindset that's lacking on the market. We were doing very large experiments, and one thing that's very obvious from these experiments is that you end up with completely different heat fluxes in those fires. It's very fundamental. If your ceiling burns, it means it's at a high temperature, so the heat transfer cannot really occur to the ceiling because it's a higher temperature than smoke. So all the heat goes in a different way. You have a much bigger heat fluxes everywhere around it. And if you think about the picture from 3 slides ago when there was a CLT car park, that's a potentially very challenging scenario for fire spread. So it's a thing that we don't discuss, but I think it should be discussed because it's another change in the compartment fire behavior that is occurring when this type of technology is introduced. And the second thing is fire resistance. I run fire resistance, and I know that when timber is in my furnace, the amount of energy I put into my furnace is much lower than when I burn other materials, because timber burns. It self-sustains the fire test. So I have to turn down my furnace to not exceed the standard conditions. because I'm testing for a standard time temperature curve. So if all the materials I test, all the assemblies I test are tested by me producing fire, and timber is tested by me trying to suppress the fire, I really struggle to put a quality sign between the fire resistance of both of them. And yet, when a non-professional, like someone without this experience, sees the papers, R60, fire resistance, 60 minutes. No small font, but they actually turned off the furnace, you know. No, it's this, and it's very difficult to communicate that this is not exactly the same. I mean, it's the same for the rating, but it's just a rating. If you rate a fish about its ability to climb trees, it's a horrible climber, right? It's about what metric is put into place. Now, the last one, the futuristic technologies, I love them. We try to develop them, one of them being 3D concrete prints. And we are very lucky to be one of the few where we actually test full-scale buildings like that. I'm not sure it's a groundbreaking technology for us today, but if you would like to build a building on Mars, perhaps sending a 3D printer there and then just arrive to a completed building is a way to go. So it's a growing technology, and again, it shows a completely new array of issues, a completely new array of challenges we've never seen before that are mostly related to the non-fire loaded parts of the building. We occur, like the middle of the building, the one next to a fire, it has beautiful properties for thermal insulation because of how the mixture is full of air and it's very nicely insulative. But we also see a very difficult and dangerous behavior on the other side, which we never had a really good other technology that would behave like this. So it shows you the need for full-scale fire testing of those things to understand how they will behave, and it's very difficult to expect that concrete mixture manufacturer would do that, for example. So here we go. We went through the innovation town. We learned about fire dynamics, ventilated facades, energy generation, electromobility, mass transit, timber, 3D printing. So let's try to find out some learnings from this. There are two possible outcomes of this talk. Either what I said was trivial to you and you are offended by me saying such obvious things, and that's one outcome. The other one, I perhaps pointed to some things where it's kind of a novelty for even the fire safety engineering community. Both are expected, and both require us to act. Because if this is trivial, then why the hell these buildings are outside there? Why have we not communicated well enough with people in power that design and build these things to stop them from doing that? It's not if the first outcome is not the lack of knowledge, it's the lack of communication, and we have to work on that as a society. If it's lack of knowledge, then we need to find out where we need to put the research money in, and we need to start researching and then communicate it properly. So regardless, is it one or two, we need to act somehow. Now, some lessons from the talk that I would like to give to you. First thing, that compliance is not safety. Compliance makes building legal. Fire engineering makes buildings safe. It's not the same damn thing. And there's a very good chance that a completely legal building is not safe. And especially in the world of innovation, where innovators would escape the legal boundaries that prevent them from innovating. They would go around the legal boundaries to put their products on the market and perhaps create legal systems that are not fully safe. The second thing, we need to think wider. We need to think about systems. We need to think about all the environment we put our products and assemblies and everything into. It's not just about the material. The producers do not have incentive to test beyond the level that allows them to put their product on the market. They very rarely do. Perhaps they should. It would be great if they did. And there are some companies that do. But most of them, they would just focus on certification and putting things on the market. When you need to understand, it's about combination of all three levels. And on top of that, considering the whole environment as a social technical system. which includes how people, technology, and organizations work together in putting that, and it also covers how we should communicate and when our things are being taken by the society. If you want to read more about social technical systems, there are beautiful works by Brian Meacham that you should read because he's covering it the best. The next thing is, if you want to measure safety of something, you need to measure it at the correct scale, assembled as it will be used in its end-use state, and in a way that is representative for the expected end use. Think about facades. They have beautiful Euroclass B. How do you get Euroclass B? You do SBI test. What's an SBI test? It's an approximation of a room corner test. What's a room corner test? It's a test that tells you how quickly the lining will cause a flashover in a standardized room. Come on, is a flashover in a standardized room the measure of fire safety of a fire in a cavity of an external facade? This is not exactly the same thing. Okay, you can use Euroclass to rank materials by Euroclass, sure. A to E, that's easy. But it's not telling you everything you need to know about the way how you use this particular product in this particular end use, and I believe here we lack the most. Then, as we are in a race, there are some things that we as fire engineers, it's obvious for us to point. We need to trust in physics. First of all, you have foam materials. They will ignite sooner because that's how heat transfer works. If you have highly insulative material, the surface temperatures are higher, energy of activation is breached sooner, it will ignite. Combustible materials in a large enough fire will burn. I mean, no matter how much fire retardants or other stuff you put into the material, if it's combustible, it's going to burn. It's just the amount of energy it needs to take to burn and sustain that burning. The material properties will change the toxic products and severity of your fire, but so will the fire environment. If you end up with an under-ventilated fire, I don't care what the soot yield of your material was, because the under-ventilated fire will create its own physics and it will create its own ways to generate toxic products regardless of the properties of your material. Then you also need to understand there's no magical solutions. If you put a thin membrane on the top of your material to pass a certain test, because it cannot penetrate this thin membrane, it's just going to do that. If it meets a small fire in a real environment, it's going to prevent, but a larger fire will destroy this membrane and expose what's behind it, which perhaps is unknown to the system, because we never tested it as a full assembly in an end-use condition. Geometry is important. Physics is important. Re-radiation and the way how surfaces react with each other, how the energy is transported from one to another, will change how materials in the cavities behave, and we will create very dangerous geometries that will lead to dangerous fires. You don't have to have a PhD in combustion to understand that if you build a cavity and you have a chimney effect and accelerated flow of air and combustible material, it's going to end up bad. So we need to be able to point this out to other stakeholders in a way that they also can understand that. And we need to question ourselves, if you find a new solution, how this change the fire environment and what does this change mean for me and my solution and my building? Ask why as often as you can. So I'm not the first or only or the best preacher of this. You need to seek smarter people than me. You need to seek knowledge. There are people that are conveying this in a brilliant way. There's Guillermo Rain, who's doing amazing research at Imperial College and had a keynote in UK a few weeks ago, which covers this in a very, very nice, digestible way. There's Frisbee, and colleagues from Frisbee are in here who are devoted to putting fire safety and sustainability together in one world. There's also my podcast where I try to interrogate people smarter than me and extract from them knowledge for you. So if you would like that way of sharing knowledge, it's open access available, and I will be very happy if you listen to it. And yeah, that's it. Thank you very much. And I'm open to questions if we have time.
Any questions? Over there. We had the appointment that I would point out 5 minutes. Wojciech was doing his presentation, I did not do that because he would have ignored me.
I would. But the guy on the back was jumping with the tablet. 4 minutes, 4 minutes.
It wasn't very interesting.
Thank you.
Yes, I agree. Thank you for that inspiring presentation. You touched upon the green facades, and
Yes.
I saw recently a post of yours on LinkedIn about living walls and a suggested solution about that you don't take the whole wall as a green wall, but you maybe compartmentalize, make compartments of that green wall. It's something I'm working on in advisory, risk advisory, and I'm wondering how far are we in making this climate change adaptation measures that are really needed possible while taking fire risk into account, because I'm struggling to find like a place where you find all the solutions that might be out there already. I was really inspired by that post of yours because I thought, that's what the municipality and the building companies are really intrigued by. What are your solutions? We're okay with that you say this is a fire risk, but how can we do this? Because we need to have this transition happening.
Yeah. So with the climate change and the built environment, I have this issue. I don't think putting green facades on the buildings is the way to solve climate change. Maybe not importing pens from China through the sea is a way. Like, I don't think we are the solution into the bigger problem. But of course, we are faced as a phase of a solution, and that it will be pushed. In Poland, the green facades are pushed because of a biodiversity and bioreactive area of the plot that needs to be there. And it says that if you want to take a bigger chunk of your plot, you need to put a green facade or green roof on there to have like 40% of the area green, whatever that means. I guess painting it green doesn't work. So how we put it, like we took this, we were unaware that it's an issue. We took these green facades in our lab. We see immediately, I was very excited for this research. I thought, I'm gonna work on plants. I'm gonna work on moisture content. In the end, I was disappointed because it's plastics and cavity once again. Like, again, the same damn thing, it's just marketed differently. And here, we already work on the world of plastics and cavities and building facades. We've learned a lot. You can break the cavity into smaller barriers. You maybe not necessarily have to put the green underneath a window. Maybe you can put it on the full wall of your building where it's not an issue anymore because it's not going to destroy the wall. It's just going to be a nasty long fire, but it will not have a severe consequences to your building. So I would say a lot matters where you put the green facade on your building. A lot matters how you deal with the cavity and the plastics. A lot matters on what precautions you have. You can put sprinklers in the cavity. You can. We also have these green walls inside compartments where they would have active fire suppression, and it also is a solution. There's many ways we can engineer this. You can affect the layers. If you're mindful about that, you can really separate the plant layer from the moisture layer in a way with some silicate clothing, and you can create much more difficult conditions for fire to jump into the cavity, and perhaps you achieve conditions in which ignition in the cavity is not that likely, and you end up in a fire-safe solution. So I guess there's a world of engineering that we can apply to this problem, and it's a novel problem. I was not aware that this is a problem a year ago. Now we're researching it, and I hopefully will present some more in-depth solutions to the problem once we finish our research on that. Though we have 3 years of funding, and we need to spend it all, 3 years. It's not going to come fast.
The time level says we have 7 minutes past the time you have, Wojciech, but thank you very much.
Thank you.
If there are any other questions, Wojciech will be here to answer the questions.
No, I will escape.
You will escape. Okay, thank you very much. Wojciech.
Thank you very much.
Yeah.